Dear students, welcome to our YouTube channel PCM Academy. Today I will discuss about some important mathematical tools that we will use in our discussion of postulates of quantum mechanics. So basically from today we will go into the details of quantum mechanics, actually the basics of quantum mechanics, that are actually the origin of quantum mechanics we have discussed till now. But from today we will discuss the advanced things of quantum mechanics, and we have to establish or we have to discuss the postulates of quantum mechanics first. But to understand the postulates of quantum mechanics, we need some mathematical tools that we will use in our later discussion. So today I will discuss about some mathematical tools. And obviously if you are new in this channel, then please subscribe this channel and share it with your friends. Okay. So basically you know that any state in quantum mechanics, any state can be described by a wave function that is denoted as more popularly psi. So let us consider that this is a wave function. You know, this psi of x is a wave function. Wave functions. Any microscopic particle, the state of any microscopic particle can be described by the wave function that is denoted by psi. So this is our wave function. Now in mathematics, this wave function actually belongs to Hilbert space, and that is nothing but a linear vector space, a special kind of linear vector space that is called Hilbert space. That is called Hilbert space, and this wave function psi belongs to this Hilbert space. So we need to know the properties of Hilbert space associated with these kinds of function. So let us consider some functions like something like psi of x, you can say, or you can say phi of x, or you can say this xi of x. So these kinds of function let us consider which are actually the member of Hilbert space, and associated with this function some number something like a, b, c. These are basically the complex number. Now we have to understand the properties of this function associated with this obviously complex numbers, together with this complex number and this kinds of functions. We have to understand the property of this. But these are not very new for you, because you can understand each and every property comparing with your three-dimensional ordinary vector space. So if you know the property of ordinary three-dimensional vector, obviously you can easily understand the property of this Hilbert space, because this is nothing but a linear vector space. This is in general a linear vector space, but you have in your 10+2 level, you know that you have your knowledge from your 10+2 level, that is the properties of simple ordinary three-dimensional vector. So you can compare the result of the property of this Hilbert space with that. So you can understand very easily. So let me tell you the first property, and that is obviously the closure property. Okay. So the first property is closure property. What it means, or you can say it is a closure relation. Closure relation. Now what it means? So if you have two functions which are the member of Hilbert space, that is psi of x and phi of x, if you add these two, then you will get another function. Let maybe this is xi of x, and if this phi of x and psi of x is the member of Hilbert space, then this xi of x must be the member of Hilbert space. As you know, if you have two vectors, one is a vector and another is b vector, these are the member of ordinary three-dimensional vector, and if you add these two, you will get another vector that will also be the member of ordinary three-dimensional vector space. So this is a closure relation. Actually, if you add any two members, you will get the third member that is also the member of that space. Similarly, if you talk about the commutative relation or commutation relation, whatever you can say, if you talk about the commutation relation, then what you will get here? Here also, if you add this psi of x and phi of x, then it does not matter that in what order you are going to add. So if you add phi of x with psi of x, or it is same as if you add psi of x with phi of x, these are same. As you know, this is obvious from the three-dimensional vector space also, if you have A plus B, that is same as B plus A, B plus A. So this relation will also be held for the Hilbert space also. Similarly, if you talk about the associative property, number 3, so let me tell you about the associative property also. Associative property. Okay. Now what this means, let me tell you first about your three-dimensional vector. So if you have three vectors A, B and C, so if you have A plus B plus C, then it does not matter if you first add A plus B then C, then it will be same as if you first add B plus C then A. So this is nothing but the associative property. Similarly, if we have three functions which are member of Hilbert space, then phi of x, psi of x and xi of x, then obviously if you add phi of x and psi of x first, okay, then if you add this xi of x, and that will be same as if you first add phi of x and xi of x then psi of x, so that will be phi of x plus xi of x, this will be same. So this is your associative property. Similarly, number 4, this is existence of inverse, or you can say the existence of 0. So existence of 0 and inverse. 0 and inverse. Now what it means, if you have a vector A and if you add this vector with 0, then we will get always vector A. This 0 means obviously 0 vector. Okay, this is obviously 0 vector. It does not matter if you give the sign or not, because you only add some vector quantity with another vector quantity. Okay, so this is the existence of 0, or you can say it is at 0 plus A, that will also be equal to A. So similarly, we have, if you talk about psi x plus 0, that will obviously be equal to psi of x, or you can say 0 plus psi of x, that is also equal to psi of x. Similarly, if you have two vector, one is opposite to other, that is if you have A vector plus minus A vector, then you will also have 0. So this minus A, if you add one vector with another and if you get the result 0, then obviously this vector will call it inverse of A. So this is the inverse. Similarly here, this inverse will also be exist, that will be psi of x plus minus psi of x, that will obviously be equal to 0. Okay, so this is a very important property that will hold always this phi of psi of x as it follows the ordinary three-dimensional vector. Okay, so now let me talk about the scalar multiplication, that we have taken the some scalar number something like a, b, c, which are basically the complex number. So let me talk about that multiplication with this vector. So these are actually called scalar multiplication, and always this will also be hold for ordinary three-dimensional vector space also. So let me talk about some scalar multiplication. Okay, so scalar multiplication. So we have the scalar quantity something like a, b, c, etc. we have taken earlier. So if you multiply a plus b with some function psi of x, that will be equal to it will be just multiply with this. So it will be a psi of x plus b psi of x. The property is very simple, but we will use this property in very complex situations. So that's why you need to understand this thing. Okay, this is basically these are the property of linear vector space, and this is your part of mathematical physics. But I like to tell you these things initially, so that you do not have any problem to understand all these phenomena that we will discuss later on. Okay, so you need these notations. Basically, this is the matter of notation. We will shift from here to direct notation. You will see. So the direct notation is very important of calculating very complex mathematics. So with using this notation, our task will be very simple. You will see later on. Okay, so this a plus b psi of x is equal to a psi x plus b psi x. in scalar multiplication. Similarly, if you multiply something like if a with psi of x plus phi of x, so this will also be just multiply with a first psi of x then with phi of x. So a psi of x plus b phi of x. Similarly, if you multiply ab with some function psi of x, that will be same as if you talk about ba psi of x. Similarly, existence of unity is also there. If you multiply 1 with psi of x, it will be same as the function psi of x, but if you multiply with 0, then it will be just 0. So these are the scalar multiplication. As you know, this is the very obvious property. Okay. So here also you will get some scalar multiplication. As you have dot product in your ordinary three-dimensional vector, here also something called the scalar product. So we have to understand the notation of scalar product and what is the definition of scalar product also. So let me talk about now scalar product. Okay. So our next topic is scalar product. Scalar product. Suppose you have two functions, one is phi of x and another is psi of x, which are obviously the member of Hilbert space. Now the scalar product can be written in this way, that is phi comma psi. And you have to remember this side, this left side, the function which is situated in left side is a complex, is actually the function itself, but this is the function itself psi, but this phi which is situated in left side, this will be the complex conjugate of phi. This bracket means actually this phi is actually phi star. This notation actually means that this phi is the complex conjugate of phi. That means it is just phi star. And it is not only just the two things which is situated one after another. This is a whole integration. This is the notation. Actually, this phi comma psi, as you know, your definition of a dot b, you know, this a dot b, what it means? It means, this is just a notation. It means that ab cos theta. Ab cos theta. Similarly, this is a notation, just a notation. What it means? It means that this is phi star. That means the complex conjugate of this into psi into dx, and the integration along the whole region. Here this is dx, so it will be along x, so it will be minus infinity to plus infinity. But in 3 dimension you can write it as dv or dτ also. Okay, but let me understand first about in very simple way. That's why I have taken here x. Okay, so this is the definition of actually scalar multiplication, and this is actually phi of x and psi of x. I have given this notation for simplicity, but actually this is what? This is this kinds of thing, phi of x and psi of x. You can write in this way also. So this is nothing but minus infinity to plus infinity phi star x into psi x dx. So this is the definition of scalar multiplication. But this, if these two are same, suppose it is phi with phi, that means if it is your phi of x with phi of x, if the scalar multiplication is phi of x with phi of x, then what it will? It will be just minus infinity to plus infinity phi star x phi x dx. Now what this is, this phi star x into phi x is mod phi x whole square. You know z star is mod z square. You know the property of complex conjugate. So it will be nothing but minus infinity to plus infinity phi of x mod square dx. Okay, so if these two are same, then you will get this kinds of equation. And let us take this is a finite number, suppose alpha. Suppose this is a finite number alpha. Now if this alpha greater than 0, if this alpha is finite number and it is greater than 0, then this phi x is known as square integrable function. So in that case, this phi of x is known as the square integrable function. This is very important. This is known as the square integrable function. Okay, so this is very important. So in general, phi with psi, this is the scalar multiplication. But if phi is equal to psi, if we take the multiplication of two same vector, that is phi with phi, then it will be just mod phi of x whole square dx. And if this is finite and is greater than 0, then obviously this phi of x is known as the square integrable function. So this is a very important property of Hilbert space. So any function which is belongs to Hilbert space should be square integrable. Okay, so this is a very important property. Now the next important thing is that norms of this function f of x. So this is nothing but the scalar product. Now let me talk about the norms of this function. Norms, okay. Norms of this function. You know, in your ordinary three-dimensional vector, so if you have a vector, that is nothing but, or mod a you can say, that is nothing but root over a dot a. This is known as the norms of vector a. Similarly here, if you want to write that phi of x, that is obviously is equal to square root of phi with phi of x with phi of x. So this is nothing but the scalar product or the dot product, and this is what? This is equal to actually root over, you know, minus infinity to plus infinity phi of x mod square dx, that we have written earlier, the notation of this. Okay, and you know, if you want to normalize this function, that means the magnitude of this is unity. So you know the definition of unity vector. So if you want to find out the normalized constant of this vector, what if you want to normalize this vector, what you have to do? You have to just divide it with its norm. So if you have n cap, suppose, or a cap you can say, if you can say a cap, so what it means? It means a vector divided by mod a. So this is nothing but the norms of a. So this mod a is nothing but root over a dot a. This is nothing but root over square root of a dot a. Similarly, we can write for a function. If we have normalization constant n, then what it will be? It will be for the what will be, this will be just if to normalize. If you want to normalize this vector to unity, you have to divide with these norms. Similarly, if you want to normalize any function which is a member of Hilbert space, you have to divide with this norm. So what that is? That is nothing but 1 upon, this is 1 upon root over a dot a. You have to divide with this. So this is the normalization constant, you can say. This is the normalization constant. Now in general, if you have a function phi of x, and if you want to normalize it, then this phi n of x, the normalized to a function, that will be nothing but the scalar product of you have to divide this function phi of x with the scalar product, that means here this minus infinity to plus infinity phi of x mod square. So this is nothing but the norms of this function. So here the norms is nothing but this is what in your vector space or in linear vector space or in Hilbert space, this will be nothing but root over, this is minus infinity to plus infinity phi of x mod square dx. Okay, so this is your normalized constant in your ordinary three-dimensional vector, and this is the normalized constants in your Hilbert space. But if this is unity, then this phi of x is obviously normalized function. If this phi of x is itself a normalized function, you don't need to divide it. So if this is actually 1, so if you talk about this if this minus infinity to plus infinity mod phi x whole square is equal to 1, that means your phi of x is normalized wave function, and this is sometimes called as the normalization condition. So that means if you have any vector in Hilbert space, and if you take the dot product or the scalar product with itself, and if you get it as unity, then obviously this phi is normalized wave function. So in general you can write it in this way also, that if phi of x with phi of x is 1, then we can say this is a normalized wave function. But if you have phi of x and psi of x, differently, if you have phi of x and psi of x, and if you take the scalar product of these two, and if you get the 0, then psi of x is orthogonal to phi of x, or phi of x is orthogonal to psi of x. That means they are orthogonal to each other. They are orthogonal to each other. As you know, in your 3-dimensional vector space also, vector space out there, if a dot b is equal to 0, you know a is perpendicular to b. A is perpendicular to b. That means a is orthogonal to b. Similarly, if psi of x with phi of x is 0, that means if you have minus infinity to plus infinity, phi star x with psi of x dx is equal to 0, then what? Then this phi of x and psi of x is orthogonal to each other. But if you have psi of x and equal to phi of x and this is equal to 1, then what you have? You have this is actually the normalization condition, or this is the normalization vector, normalized to each other, or you can say that normalized to itself actually. But if you have the scalar product of this phi of x and psi of x, and if this is equal to 0, then phi of x is orthogonal to psi of x, or they are orthogonal to each other. And we can combine these two property in one sentence. How we can write it? You can understand easily that if you write some phi of x with psi of x, some phi of x with psi of x, instead using this notation, if we use that phi I and phi j, the dot product, we can write this dot product in this notation. And if you get this as 1, then what you can say? You can say this is the normalized to each other. This is a normalized wave function. And if this is 0, then they are orthogonal to each other. And when it will be 1, when I is equal to j, and when it will be 0, when I and j are different, I not equal to j. Okay, so this condition is known as orthonormal condition. Orthonormal condition. Normal condition. And you can write it by using the Kronecker delta notation, that is nothing but phi I with phi j, that is equal to nothing but delta ij. Delta ij. And you know that delta ij is equal to 1 when I is equal to j, and it is 0 when I not equal to j. So we can use this property of Kronecker delta here. Okay, so phi I with phi j is equal to delta ij means this is the orthonormal wave function. The orthonormal wave function, that is orthogonal as well as normalized to each other. Okay, now please remember that this is nothing but you should not forget always that this is just the short notation of the integration. What integration is this? This means actually I have written many times that this is nothing but phi I star phi j into dx, which is run from minus infinity to plus infinity, and that is actually equal to delta ij, you can say. So this is the orthonormal condition. Okay, now we can convert the whole theory that we have discussed till now, the mathematical tools that we have discussed till now, we can convert this whole thing in another representation, that is called the Dirac notation. So in the next class we will discuss the whole thing with the help of Dirac notation, that you can understand. And that Dirac notation, that is the bracket notation, is very useful, that we will use our further topics when we will talk about the postulates of quantum mechanics. Okay, so for today, thank you.